Vision IB, where physics becomes clarity.
So, hello, my dear students. Today's our first lecture will be on thermodynamics. It will be an introductory lecture, and I will be teaching you about the basics of thermodynamics, why thermodynamics is used in our and how, like why thermodynamics is used in many of the industrial application, what are its application, and why do we use and why do we study thermodynamics. We will be covering all those basic things about thermodynamics. Secondly, after covering all those basic things, we will learn about the zeroth law of thermodynamics. We will also learn about the first law of thermodynamics, and we will learn some interesting concepts about some interesting concept related to heat, work, and internal energy. So before studying any topic, it is a mandatory thing to understand why why we study thermodynamics and why we study things. So before, just make it a habit, before you study any topic, just keep in mind why you need to study that topic. Where is the application of that topic? So let's getting any delay further, let's start with our first topic, that is our introductory lecture on thermodynamics. So let's begin with some basic things in thermodynamics. So here we have, as I move on to the next slide, we have the real life applications of thermodynamics. So the question comes, like, we study thermodynamics, we have heard about thermodynamics a lot, but where do these things really find its application in? Where do we use these things? So like this question is like really mind boggling for students. They don't understand where do we use these things. So from my perspective, before starting the chapter, we should first understand where do we have this application and where do we have this application of thermodynamics in real life. So if we have to look at it, it has its major application in engineering, industrial, everyday life, right from biological to medical devices, everything in environment and in space and advanced technology. So if you look at it, everywhere in all the areas of science and technology, there is a real life application of thermodynamics. So if we were to look at in engineering, like if we were to look in engineering, what applications do we have? Like whatever, wherever you see turbines, gas compressors, power plant, refrigerator, air conditioning, everywhere you see, everywhere there is an application of thermodynamics, right? So if we go for the industrial level, all the chemical reactors in the industrial level, all the petroleum refining setup, all the metallurgy and food processing setup in industry are based on the laws of thermodynamics. So if you go for the everyday life, if you look at everyday life, right from cooking to pressure cookers, I hope everyone knows what pressure cooker is. Right from vehicles, heaters, insulation device, and cooling, everywhere we find a use of thermodynamics. Even a biological and medical application is no more away from thermodynamics. Like thermodynamics has its application in biological and medical also. Like if we were to look at the human metabolism, all the human metabolism is based on the laws of thermodynamics. Even the body temperature control, medical devices, and in some advanced application, if we go, we can see its application in cryogenics. So cryogenics is the process in which the object is cooled to a very low temperature. So like it's an advanced application in biological and medical field. So if we look at the environment, all the climate change, renewable energy system, waste heat recovery, so all these are the most famous examples of real life application of thermodynamics. So in space and advanced tech, you already know that in spacecraft, thermal control system, rocket fuel system, nuclear fuel cells, everything has its application in thermodynamics. So from all these examples, we can say one thing, that thermodynamics is a very important branch of physics that we need to study, right? So I hope you guys understood where we have the real life application of thermodynamics. Now let's move on to other slide and see it. So the question comes, why do we study thermodynamics? Why is there any need to study thermodynamics? So whenever whenever there is a concept of heat, there is work, there is energy, heat and work are central to all engineering processes, right? So whenever there is application of heat, where there is application of energy, when there is application of heat, and where there is application of work, all these things, wherever these things are, we have to study the thermodynamics, right? Because we need to study thermodynamics because it is a foundation of all machines and systems, and whatever machines that are around us, right from all the turbines to the plane engine to the car engine, everywhere these machines are involved. And wherever there is machine, heat, energy and work is involved, we can say that thermodynamics has its application. So in order to study all those machines, all those heat system and everything, we need to study thermodynamics, right? So like it's the same slide, like it's the same thing, nothing much more different than the previous slide. So as I said, it has application in industry, engineering, industry, medicine and environment, and even in daily life activities like cooking, transport and cooling. And the one of the most important reason why we study thermodynamics is because it gives us insight into natural phenomena. Like it helps us to understand how the heat flows. Now we know that if you have studied thermodynamics, you know that the heat always flow from hot system hot system to cold system. So this is because of thermodynamics we are able to understand these things. So because of all these systems, because of all this importance of thermodynamics in many of the things, we have to study thermodynamics, right? So just keep in mind from this slide, we can just conclude that wherever energy, heat and work is involved, wherever these things are involved, energy, heat and work is involved, we have to study thermodynamics, right? So I think everybody is clear with why we study thermodynamics and the real life application of thermodynamics. Now let's move on to another slide and see what we have. So the question comes, what is thermodynamics? Like we solved two questions, we already studied two things. First, the real life application of thermodynamics. Second, we studied why do we need thermodynamics, why do we need to study thermodynamics. And the third one before starting thermodynamics is, what is thermodynamics? So if we were to look it in simple words or in the layman terms, thermodynamics is a science and energy and a science of energy and its transformation. Like it's a science of energy and how the energy is transformed from one form to another form. It also studies the relationship between heat, work, temperature and energy in many of the physical engineering system. So if we were to look at thermodynamics, what are the basics fundamentals of thermodynamics? So thermodynamics is based on like some basic laws which include the zeroth law of thermodynamics that we will study first. Second, that will be the first law of thermodynamics. Third will be the second will be the third will be the second law of thermodynamics, and the fourth law will be the third law of thermodynamics. So all these laws are pretty important, but I guess we will start first with the zeroth law and then with the first law of thermodynamics. In this lecture we will cover zeroth law and first law. Second law and third law we will be covered in the next lecture of thermodynamics. Whenever I upload the video, you will be able to see it. So I'll upload it soon, so like you don't have to worry about that. So what does thermodynamics basically explain? So if we were to look in detail, it explains us how the energy is conserved, how the energy is converted, and how the energy is transferred. Just look closely. How it says, how can we conserve energy, how can the energy be converted, and how can the energy be transferred. So study, so all this explanation is being given by the thermodynamics. All these answers, all the answer to these questions is based on the study of thermodynamics. That is the big reason why we need to study thermodynamics. So as like it's the same thing, like where do we find its application? So as we have already studied, we find its application in engine, power plants, refrigeration, biological process, climate change, and space technology, as we have already studied in the previous slides. So it is the same thing. So hope now you understood what is the real life application of thermodynamics, why do we study thermodynamics, and what is thermodynamics. So you might be thinking like, why I'm explaining you all these things, and why not I just start the lecture? Because I believe it is like science is not just for scoring marks and getting good grades, it's for understanding the things, it's for your own static happiness. Like if you feel happy, you must feel happy about learning something, like, and you must know why we are learning something and why we are learning this, and what, like whatever I am learning, does it have a real life application? So that is the big reason why I explained you the application, and why do we study thermodynamics, and what is thermodynamics. So let's start with today's lecture on thermodynamics. And so let's begin. Let's see. So thermodynamics, what is thermodynamics? So if we were to look at the definition of a thermodynamics, it says it's a branch of physics that deals with the concept of heat and temperature. So just keep in mind, wherever the concept of heat and wherever the concept of temperature is there, we have to study thermodynamics. That system, in that system we will have to study thermodynamics. So basically, in the simple terms, it's the physics that deal with the concept of heat and temperature. So wherever heat and temperature is involved, thermodynamics will be involved, right? So let's start the basics of thermodynamics. So starting with the basics of thermodynamics, thermodynamics is based on two systems. Like if we study thermodynamics, it has based on the concept of system, and second, it is based on the system of surrounding. So like you might have already studied what is system and what is surrounding. So if I say this is earth, this is our earth, this is our planet earth. Sorry, I'm making it green because I want earth to be green. And so the thing that we study, the specific part of the universe, that we study is called system, and the rest of the part is called as surrounding. So rest of the universe is surrounding, and we are studying about earth, so earth becomes the system. Okay, so now you understood the basic thing, what is system and the surrounding. So if you look at the explanation, like what I said, I'll explain you it in a simple word. So whatever the specific part of the universe that we study, so for example earth, this is the specific part of the universe, so this is called as system, and everything outside the system that interact with it is called as surrounding. So hope you are clear with the concept of what is system and what is surrounding. And now we will study about the boundary. So boundary may be imaginary surface or the real surface that separates system from surrounding. So have a look at it. Suppose this is the earth, uh, this is the atmosphere, and the rest of the part, is universe, right? So we can call earth as a system, that is the specific part of the universe that we will study. See, this atmosphere separates earth and the universe from each other, so we can call it as this atmosphere of the earth as boundary, and the remaining universe is called as surrounding. So hope you are clear with the concept of system, surrounding, and a boundary. I don't think that it is ever difficult to understand this, but hope you understand what I'm trying to say in this, right? So let's study a boundary in detail. So before studying boundary, we will study about thermodynamic equilibrium. So a system is said to be in thermodynamics equilibrium if it is in either one of the three states, either in thermal equilibrium, chemical equilibrium, or the mechanical equilibrium, right? But since we are since we are studying thermodynamics, so I will consider thermal equilibrium to be our topmost priority that we will study. So thermal equilibrium is of utmost priority when we are learning thermodynamics, especially for IB physics. Okay, so now we will learn about thermal equilibrium. So let's see what is thermal equilibrium is. So two systems are said to be in thermal equilibrium if the temperatures of the two systems are equal. Suppose I have system A and I have system B. If both of them have same temperature, if the temperature of both of the system is same, we can say that two of the system are in thermal equilibrium. So hope you understood the concept of thermal equilibrium. We will also cover the concept of thermal equilibrium while studying the zeroth law of thermodynamics, in which it will be more clear to you. Just for now, just understand, like, if there are two systems and two systems have same temperature, then we can say that two systems are in thermal equilibrium. Now again, I would like to explain you the concept of system, surrounding, and wall. So you have already I have gave you the example of earth, atmosphere, and the rest of the universe. So earth is a system. The atmosphere we see around it can be defined as a boundary, and the remaining thing that we see around and the rest of the universe that we see can be considered a universe. So let's move on to other slide and see. So as I talked before, as I had as I explained before, there are two types of wall. So wall can be of like a diathermic wall or the adiabatic wall. So what is a diathermic wall? So if we look in a simple terms, a boundary that allows heat transfer between system and the surrounding is called as diathermic wall. For example, you can see the example of a diathermic wall of a cup of tea and the surrounding. So this is a cup of tea. This cup of tea has a diathermic wall. So what is diathermic wall? A diathermic wall is something that allows heat transfer between the system and the surrounding. So if we look at it, the tea inside it is a system. The cup, the surface of a cup is a boundary, and the remaining area is surrounding, right? So what is happening here? Since the wall of the cup is diathermic, like when we put the cup initially on the table, it was hot, but after some time it went cold. So what is happening here? What has happened here? Actually, because of this diathermic wall, there was a heat exchange between system and the surrounding, and due to that heat exchange, both system and surrounding went into an equilibrium state, and because of that the tea becomes cold. So this is diathermic wall. Now, if you have studied thermodynamics already, you must be well aware with what is adiabatic wall, right? So you are already aware with the adiabatic wall. But if we were to look, if for the someone who is new and who is revising thermodynamics, for them I would like to explain an adiabatic wall is a boundary that does not allow any heat transfer between system and a surrounding. So there is a system A, and this is the surrounding. So if I put a adiabatic wall between the system and the surrounding, there will be no heat transfer between the system and the surrounding. Why? Because the wall is adiabatic. This wall is preventing heat flow between the system and the surrounding. Best example of an adiabatic wall is a thermos, where you keep your hot coffee usually. So it is not 100% adiabatic. The coffee will cool down eventually. It won't like last forever. It won't keep. It won't disallow the heat to move forever, but it will help for some time. So if we look at the thermos bottle, the wall of this thermos bottle, this wall that I have marked here on the screen, this wall over here, this wall is adiabatic wall. So now what is happening, if you put a hot coffee inside it, if you put a hot coffee inside it, what will happen is no heat transfer will take place between the system and the surrounding. And why no heat transfer will take place? Because there is an adiabatic wall between them. So so thermos is the best example of adiabatic wall, which does not allow heat transfer to take place. So now I think you are clear with the wall. Like there are two kinds of wall. One is diathermic wall and second one is adiabatic wall. Now, after we have studied all of this, we have studied thermal equilibrium, we have studied the type of wall, we have studied system and surrounding, we have already covered the basic definition of thermodynamics. We also studied about the real life application of thermodynamics. I think after covering all these things, you guys are ready for the first law of thermodynamics. And it seems complicated, but trust me, it is very simple. So we will, sorry, not the first law, we will study with the zeroth law of thermodynamics. And it may sound complicated, but it is not complicated at all. It is very simple and a logical thing. So let's move on to the first law of thermodynamics. Let's learn about, sorry, not the first law, zeroth law, my mistake. So now let's learn about the zeroth law of thermodynamics. And why learning about the zeroth law of thermodynamics is very important. So why do we study the zeroth law before the first law? Like I could have started with the first law of thermodynamics. No one covers the zero law of thermodynamics, but trust me, zeroth law of thermodynamics is very important whenever we study thermodynamics. So if we look at it, if you look at my screen, if it is visible to you properly, so zeroth law defines the concept of temperature and establishes a condition for the thermal equilibrium. So zeroth law is very important when considered from the thermal equilibrium point of view. So because it includes the concept of thermal equilibrium, and without zeroth law, first law of energy, like first law of thermodynamics is like very difficult, or it will be very absurd. You won't understand it properly, right? So that is why I decided to teach you the zeroth law of thermodynamics, because just think, without understanding the concept of temperature and thermal equilibrium, you cannot apply the first law of thermodynamics to any of your understanding. Because as we clearly know, the first law of thermodynamics relates with heat, work and energy. So this is the reason we study zeroth law, because it provide us with the thermal equilibrium concept and also helps us to understand the concept of temperature. Hence, we can say that zeroth law is the foundation of all the other laws of thermodynamics. So I think you are clear with this. So let's move on and see the first law of thermodynamics. So by the definition, you can see here, if two systems are in thermal equilibrium with the third system separately, then they are in thermal equilibrium with each other. Let's assume there are three systems: system A, system B and system C, right? If system A is in thermal equilibrium with B and system A is in thermal equilibrium with C, I can surely say that system B is in with thermal equilibrium with system C. Why? Because this is the zeroth law of thermodynamics. This is what it states. So if suppose the temperature of A is 45 Kelvin, temperature of B is 45 Kelvin, so they are in thermal equilibrium. Similarly, temperature A and temperature system A and system B are in thermal equilibrium. So if A is 45, C must be 45. So if A is in thermal equilibrium with B and A is in thermal equilibrium with C, we can say that both B and C are in thermal equilibrium, and we can say that this whole system is in thermal equilibrium. So hope you understood this zeroth law of thermodynamics very clearly, right? Let me explain you this more with a bit more example. I have this system A, here we have this system B, here we have this system C. Now, as I have explained you two types of wall, adiabatic and diathermic wall. So we will apply that concept of adiabatic and diathermic wall in this example. So between B and C, we have adiabatic wall. Between A and BC, we have this diathermic wall. Now just listen carefully. What is happening? As we know that if there is an adiabatic wall between the two systems, there can be no heat exchange, right? No heat exchange. But since A, B and AC have a diathermic wall within them, so there can be a heat exchange between AB and AC. So because of this heat exchange, what is happening is A comes in thermal equilibrium with B, and A comes in thermal equilibrium with C. Now, according to the zeroth law of thermodynamics, I have already explained you that if A is in thermal equilibrium with B and A is in thermal equilibrium with C, then both B and C will be in thermal equilibrium with each other, right? So let's now flip the situation. Now I have this system A, system B and system C. Now if I put a diathermic wall between A and B and C and an adiabatic wall between AB and AC, we can see that despite of putting the diathermic wall between B and C, there is no heat exchange between them. And why there is no heat exchange between them? Because they are already in thermal equilibrium, right? Because of the previous example that I told you, because of that, A was in thermal equilibrium with A was in thermal equilibrium with B and A was in thermal equilibrium with C. So now B is in thermal equilibrium. So that's why we say that B is in thermal equilibrium with C. So hope you understand what I tried to explain. If you find anything confusing in this, please comment on the video and just let me know. If you find something confusing, I will try to answer all those questions. But I don't think it is even that complicated to understand it, because I have tried to explain you this in the simplest possible manner. So friends, state variable are the properties that define the condition of a system, and it is independent of the path taken, right? So let's assume you have to move from point A to B. So there are many ways where you can move from point A to B. There are many paths, but state variable is not dependent on the path. It depends on whether you have reached from point A to point B. This is just a general example. Don't consider it as a standard example. I'm just telling you that it does not depend on the path taken of a system. It depends only on the present state of a system. So like for example, if you have a look at it, look at this example. In this, a 30 degree of water has same state whether heated slowly or quickly. So water will be in same state whether you heat the water slowly or whether you heat the water quickly, right? So if we were to look at about the state variables, there are two different state variables. First, the intensive state variables, and second, the extensive state variables. So what are extensive state variables? It indicates the size of a system, and the intensive state variable does not indicate, never indicates the size of a system, or you can never assume the size of a system based on the intensive variable, but based on the extensive variable you can assume the size of a system. For example, what are the extensive variables? For example, volume can be considered as an extensive state variables, while mass can be considered as an extensive variable. Internal energy can also be considered as an extensive state variables. Internal energy, we will cover it later in detail. I'll explain you what is internal energy. It will be uploaded in the next video lecture, but for now just understand there are two types of variables. One is extensive variable, second one is intensive variable. So from volume we can say that the system is big or small. Like if something has large volume, it is big. If something has small volume, it is small, right? Similarly, if something is more heavy, its size might be big, and if something is less heavy, its size might be size might be less. So based on volume and based on mass, you can make an idea of what is extensive variable, right? Similarly, if we were to look it into the detail of intensive variables, so what are intensive variables? Intensive variable do not indicate, they never indicate the size of a system. For example, just by the pressure and temperature you cannot assume the size of a system, right? They will not, like, it is like very like impossible to determine the size of a system. So from pressure and volume you cannot never assume the size of a system, right? So these are the state variables, and these are like intensive and extensive state variables. Now as I have told you, I will cover the concept of internal energy in the next video, but I think I should continue this in this video only. And let's have a look at the concept of internal energy. So internal energy, it's a very important concept in physics. So internal energy is a thermodynamic state variables. So you might all be aware of what is kinetic energy and what is potential energy. Right, so you might be clear with what is kinetic energy and what is potential energy. So kinetic energy is, like, if you look in simple terms, it is the energy possessed by the virtue of motion, and the potential energy is the energy possessed by the virtue of its position, right? So if we were to look at the internal energy of a molecule, internal energy of a molecule is the sum of kinetic energy plus potential energy of the molecule, right? So what is the kinetic energy of a molecule? These molecules have random atoms, and they just jiggle around each other, right? So they jiggle a lot. So that jiggling is called as kinetic energy, while the bond between those molecules, like bond between those atoms or molecules, is called as potential energy. How strong the bond is between the atom or molecule is called as potential energy, and the energy by which the uh, atoms vibrate is called as kinetic energy. So kinetic energy is basically so internal energy of a system is sum of kinetic energy plus potential energy, right? So I hope you understood the concept of internal energy, and studied the concept of state variables. Why do we study thermodynamics? Hope you understood about the zeroth law of thermodynamics. If you have any confusion regarding any of these topics, whatever I taught you, you can please ask me in the question section, and please like and subscribe to my channel.
If this helped you understand physics better, like the video, share it with friends, and subscribe to Vision IB.